Welcome to a special 15-year anniversary episode of Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today it's my pleasure to welcome Saniya LeBlanc, Professor of Mechanical and Aerospace Engineering at George Washington University. Saniya's research lies at the intersection of material science, energy conversion, and thermal transport. Her research includes the development and demonstration of improved energy conversion technologies involving advanced materials and nanomanufacturing processes. Saniya, thank you so much for taking the time to talk with us today. Can you tell us a little bit about yourself and how you first got involved in nanotechnology?
Sure. So I am currently an assistant professor in the Mechanical and Aerospace Engineering Department at George Washington University. And prior to becoming a professor, I was a research scientist at a startup company in the Bay Area working on developing thermoelectric devices for waste heat recovery. It's hard to really say when I got my start in nanotechnology. When I was an undergraduate, I actually started doing research in microelectromechanical systems. And at that time, micro was the big thing. It's where a lot of work was going on. And I got, I would say, my foundation for understanding what people now call nanofabrication. I got that during the research experience I had doing them. So that's when I really learned how photolithography works, how to think about design when you are using clean room type fabrication processes to make devices. And I think that was influential in pushing me towards the smaller length scales. And then in graduate school, I was very interested in thermal transport. How do energy carriers move through materials? And what does that mean about how heat is transferred in materials and in systems? And that necessarily occurs at the nanoscale. So I didn't set out to be in nanotechnology so much as the energy carriers that I was interested in, they move at the nanoscale. And so if we're trying to impact how energy is transported, then we have to impact those carriers, which means that we have to do engineering of systems and materials at the nanoscale.
I know that your group is looking at selective laser melting for thermoelectric materials. Can you tell us a little bit about this additive manufacturing technique?
So I had not set out to do additive manufacturing, but what has happened in thermoelectric devices is that as people have engineered the material, often by doing nanostructuring of the material to improve its transport properties for thermoelectrics, those improvements in the material were not being realized at a device level. And that's because when you think about how heat is moving through the entire device, you realize that you actually start having to engineer extrinsic properties, not just intrinsic properties of materials. And that means you have to think about how you can actually make adaptive geometries that allow you to control how heat is transferred through a device. The current manufacturing technique for thermoelectric devices actually doesn't let you design that geometry. You can't manufacture a wide range of geometries so that you can create structures that allow you to control thermal transport and heat transfer within the device. So I said, why is that? And I really saw that the manufacturing approach didn't allow you to change the device design. And I set out to look for a manufacturing approach that would allow us to change that. And that led me to additive manufacturing, because with additive manufacturing, it's this free-form process where you can create a structure that maybe is very complex or has a lot of hierarchical structuring. And you can then start to adapt the geometry to what it is you want your device to do. So I thought, okay, additive manufacturing actually might offer a lot of benefits for thermoelectrics. And I looked at the various additive manufacturing techniques. And what we settled on for various reasons was laser additive manufacturing approach. And so in this approach, you build up a part layer by layer. So it's just like a on the bench type of 3D printer, but it's a technique that is used for materials like metals or ceramics. And so you lay down a powder of that material on a very thin layer, and you take a laser and you melt it in the pattern that you want to create. And you do that layer by layer. And so when you do that, you can now build up a geometry that is very complex. And you can do that by having just very, very thin layers that you're melting at a time, and then you melt each layer to the layer before it. that was really appealing for trying to change the geometries of thermoelectrics. And so that's how we set about doing it. And what was really interesting is I went to the additive manufacturing community and I said, okay, can you just tell me who's doing this additive manufacturing process on energy conversion materials like this? And it turned out no one was really doing it. And then I thought, well, that's even if this doesn't work, it's going to be a really fun project. And so we've been doing it for about 5 years now and have gotten the technique to work on thermoelectric materials. And we're looking at how does this additive manufacturing process maybe change the structure of the material? And is there a way to actually exploit that so that we can improve thermal and electrical transport in the material as it's needed for a thermoelectrics application?
So I want to switch gears a little bit. And I know that we share a passion for working with students, education, and promoting opportunities for undergraduates in particular. And I'd like you to share a little bit about how you have worked with undergraduates and provided them opportunities through, for instance, the Nano Fellows program that you ran, and also the introductory seminar course that you offer.
Yeah, this is a topic that I'm really excited about. I think in my heart, I am an educator. I love being a professor because I can combine being an educator with my other passion, which is engineering. When I first became a professor, I saw this opportunity funded by the National Science Foundation that was asking for innovative ideas related to how to incorporate nanotechnology education into undergraduate education. So a lot of nanotechnology education is done at the graduate level. So you take those courses, you get to do those kinds of research projects when you're in graduate school, but there aren't as many opportunities at the undergraduate level. So I thought this was really interesting, very germane to the issue of how do we actually prepare undergraduate students for jobs in emerging technologies. And the idea I had was that we maybe shouldn't try to create another minor because our engineering curricula are so packed. And I know this is true across the board for engineering majors. There are already so many courses that students have to take that to add multiple nanotechnology classes to that was just going to be very difficult for undergraduates to try to work into their own curricula. And so I thought maybe we could tackle this by doing a really focused summer program where undergraduates got almost a crash course in nanofabrication, characterization techniques, and also monetization, ideas around how do we translate nanotechnology developed in the laboratory out into the commercial world. Along with a couple of my colleagues, we designed a program where over the course of 8 weeks, students got just that. So they got tutorials in the morning that were just mini crash courses on material science as it relates to nanomaterials and nanofabrication and nanofabrication techniques, lithography, all kinds of topics that are relevant for nanotechnology. They would get a little crash course in the morning, and then in the afternoon, they would get the training. They would learn how to do it. So they were using the electron microscope, using the atomic force microscope. They were doing electron beam lithography. They were kind of getting exposure in a meaningful way to what we felt were kind of the core skills and ideas that they needed to encounter. And they also got to do a short research project where they got to choose whether they wanted to focus on the fabrication, characterization, or monetization aspect of nanotechnology. And so the seminar course is something that we developed that would be relevant for both students who wanted to do the in-depth summer program, as well as students who just wanted a little bit of a taste of nanotechnology, so that because they don't get that exposure at the undergraduate level, they could take a 1 credit hour seminar course where we really just hit on the basic ideas of nanotechnology, fabrication, characterization, and monetization. And students get that exposure, and then they could choose, okay, was that something that just improved their overall science literacy? And that's great. It increased their knowledge. Or is it something that really opened a door for them and they wanted to pursue it further? And so we would give them options. They could do the Nanotechnology Fellows Program. They could do undergraduate research with a professor. We talked about opportunities in terms of going to graduate school.
And I think that the students that I've talked with have been really thrilled with the experience. And I think that that's exciting. Thanks for sharing that with the listeners. I want to take you another step in that direction, and that is the work you've done discussing nanotechnology with the general public.
Yeah, so I have done this. I would say I kind of explored the idea more than anything else. So where we have been most active is the Nanotechnology Fellows, who are undergraduate students that have done that program with us. They will participate in workshops and outreach sessions where we have high school students come to GW, George Washington University, and participate in a half-day session where they get to do activities related to nanotechnology. And that's something that our undergraduate students lead, those activities. So I certainly facilitate the workshops happening, but we do a fair amount of prep in advance so that the undergraduate students are prepared to then do this interactive teaching, mentoring experience for the high school students. And so actually, before I went to graduate school, I was a high school teacher in Washington, D.C. through a program called Teach for America. And so we each year have had a group of high school teachers and students come from the high school where I taught, and they come and participate in these workshops that the Nanotechnology Fellows do. And we've also done workshops with Georgetown Day School, which is a school in DC, where they do a STEM outreach day. So students from across DC come and participate in workshops to learn about different STEM topics. So we've also done workshops with that. So that's some of the outreach that I do. I think because of my history and working with high school students, I have a particular interest in that and working with that population, both high school students and teachers. So I think that's where, in terms of reaching the broader public, I spend more of my outreach time. One of the other things that I've done is tried to understand what the role of nanotechnology as a topic is in the science literacy that the general public should have. So I had this question about whether or not nanotechnology is something that the general public needs to know about. And if so, how would we go about teaching them about nanotechnology? I mean, what are the ways that we would do that? And what impact does that have on people's ability to think scientifically so that even if they don't remember the specific facts about nanotechnology, is there a way to use nanotechnology to actually influence the ability of people to think critically about scientific topics? So that's something that I'm actually really interested in. I haven't necessarily found an answer to that, but I have looked through literature related to media and communications, education, and nanotechnology, and tried to bring that all together.
With respect to nanotechnology research and development, we often hear the interdisciplinarity in collaborations across different areas has really been pivotal in the advancements of nanotechnology, and that's one of the things that the NNI has done is bring different communities together. Has that been the case in your research?
Absolutely. Absolutely. I cannot emphasize that enough. I would say that in a lot of the work that we do, so for example, we have a project related to carbon nanomaterials and how to integrate carbon nanomaterials into inks that you could print with an inkjet printer and make then, for example, flexible electrical devices out of what is a sustainable, fairly low cost nanomaterial. And for that project, it's a collaboration that we've done with a professor in chemistry at George Washington University. And that PhD student, who's a mechanical engineering PhD student, has had to learn and teach me so much advanced chemistry about dispersions and colloids and interface science. And, I have to say, I haven't taken chemistry since I was an undergraduate, but it doesn't change the fact that I need to know it for the work that I'm doing. So I would say, I encounter this issue of always needing to know information from a discipline that I'm not trained in, where I'm having to collaborate with people, learn from them and work with them so that we can bring lots of different disciplines together to solve a particular problem, because the problem doesn't realize that there are different disciplines. So we certainly do a lot of interdisciplinary work.
So I want to look to the future. So when you consider some of the challenges that are facing the U.S. and the world, where do you think nanotechnology will likely play a role in solving challenges?
Well, I think nanotechnology is going to be present in probably the majority of emerging technologies that are going to impact society. Where I think we will perhaps see it the most, where it will be the most evident to us, will be in health and medicine. And that's actually not even an area that I'm in quite yet, but through the nanotechnology seminar course and the nanotechnology fellows program, have learned from students' research and project about how prolific nanotechnology is in medicine and how close so many of the technologies are to being incorporated into devices and techniques that we are already using and will be using in the near future. So I think in health and medicine is where I see some of the biggest impacts that we will see from nanotechnology. The other one I do think is in energy, as it relates to materials and materials development. We are becoming more and more knowledgeable and skilled about how to structure materials at the nanoscale in order to get materials to do what we want them to do. And in energy, that might mean, for example, converting one form of energy into another, converting a form of energy that we're not that interested in using into one like electricity that we are very interested in using. And so I think that the impact of nanotechnology on materials development and the new materials impact for our energy efficiency, our abilities to convert energy into forms that we use most, that's going to be really profound for us. And we have, I haven't been at this for too long since I'm fairly early in my career, but what I've been able to see in just the past 10 years related to the impact of nanotechnology on materials development has been really amazing. And I think that we are at the point now where we're seeing some of those technologies get out into society. And I don't know that everyone realizes that there's nanotechnology embedded in that. And so I hope they realize that these new materials with new capabilities have this nanotechnology aspect to them.
I want to thank you again for taking the time to talk with us today and ask you, do you have any closing thoughts that you would like to share with our listeners?
I think what I'd like to share is something that I'm passionate about. I think you're passionate about. It's that the curiosity that people innately have, I would like for people to recognize, especially young people, to recognize that curiosity is something that they can nurture if they go into science and engineering. There are challenges, certainly, but those challenges are exciting. And what we can do with the technologies that we develop have a direct impact on society, on our quality of life, on our ability to make things that have never been made before. All of that comes from science and engineering. And so nanotechnology is one aspect of that. But for anyone who might be listening, I think that science and engineering is often daunting. And I'd like to just really point out how it is about being curious. As daunting as, some of the classes might be, it's about being curious and wanting to have an impact on society.
Thank you for joining us today for this special 15-year anniversary edition of Stories from the NNI. If you would like to learn more about nanotechnology, please visit nano.gov or email us at info@nnco.nano.gov. And check back here for more stories.